My talk today will be about the importance and the benefits of the SHM in general for the aerospace industry. But in contrast to Oscar, I will go a bit into the more technical details, and I will present a case study to demonstrate what benefits we can have and what challenges we are facing at the moment. Why is SHM in aerospace important? So composite structures have been used extensively more in aerospace structures for structural elements and recently also for the engine blades. The issue with composite materials is that they have complex failure behaviors, and usually this is not completely understood. And especially when we take into account also impact damage, which is extremely critical for composites, this can create degradation that is difficult to monitor and can be critical for the safety of the structure. For that reason, we need the novel structural health monitoring systems in order to accurately monitor this degradation process. What the SHM can provide, however, is that we can use the output of SHM to develop diagnostic and prognostic algorithms, which in turn will help in decision making for maintenance, and then eventually shift from the preventive or corrective maintenance actions to a full condition-based maintenance scheme, which will reduce costs and improve availability and safety of aircrafts. The two level of SHM, as I already told you, is in first diagnostics, which focuses on detecting, identifying, locating, and quantifying the extent of the damage. And after that, we move to level two, which is the prognostics task, which usually refers to estimating how the damage is going to progress through time, given certain loading conditions, and evaluate the residual strength or predict the residual strength, or even predict how long this part will survive given certain loading conditions. Some state-of-the-art SHM technologies include fiber optical sensors, which are primarily strain, temperature, or vibration sensors, and this can be broadly classified into the distributed fiber optical sensors and the FBG fiber optical sensors. And then we have the piezoelectric transducers, which mainly use elastic wave propagation and vibrations to monitor different things. These sensors include accelerometers, acoustic emission sensors, and active lamp wave sensors. So why SHM? SHM can provide online monitoring and degradation information that can be used for diagnostics and prognostics, which using expert knowledge, decision-making, and predictive maintenance actions. And predictive maintenance, we can go to a condition-based maintenance scheme, which will in turn increase safety, availability, and reduce cost and increase the sustainability because less waste is going to be present. However, what we are missing at the moment is ground truth information of the damage, and extensive data pre-processing is usually required in order to extract this meaningful information. The next two, implementation and integration, focus on how we are going to implement and integrate these SHM systems into new or current applications. In order to demonstrate that, we're going to use a case study on a foreign object damage panel. This is something that OEMs use to verify the integrity and how good an engine blade can withstand damage. So this is part of a sub-part of the newer LEAP engine blade, and it's comprised of a 3D woven composite body with a metallic leading edge, and eventually this led to a reduced panel which had the curved surface with dimensions of 350 times 800 millimeters and a varying thickness between 2.8 and 10.8 millimeters. So in this case study, we had two different SHM systems. So PCT transducers, which we had the novel printed PCTs and ceramic PCT sensors, which you're going to be hearing in the next presentations, and we had 5 arrays at 5 locations, as can be demonstrated in the figure over here. In addition to that, we had surface bonded and embedded FBG sensors. However, unfortunately, due to the shipping and the resin transfer process, most of the embedded sensors did not survive, and we will not be talking about this during this presentation. The experimental setup that we implemented is a 4-point bending test according to an ASTM standard in order to evaluate the flexural properties. And the test that we decided to do was a low frequency fatigue comprised of triangular load and load cycles. And the tests were run until collapse. The loading, including an increased severity loading, in order to implement more severe loads over the course of time and see how well the damage is going to progressively grow over time. The test was run in blocks, so each block is 200 cycles for a total of 400 cycles per load, and it's posed every 200, 150 cycles for lamp wave measurements, which, as you can see over here, changed depending on the severity. We also performed impact damage prior or in situ testing of approximately 50 to 60 joules in order to have an initial abnormality and monitor its growth over time. Comparing to the regular quasi-static test that was just used to evaluate the collapse load, we observed that the fatigue failure load was on average approximately 15% lower. So instead of 28, which was the quasi-static load, we had failure around 24 to 26 kilonewtons, with an average lifetime of 3,200 cycles. The main damage modes were skin tearing, which can be barely seen in this picture over here. So this was usually the first that was observed. And then we had fiber and skin breakage across the width of the panel. And this was accompanied usually by some damage on the exterior shell of the FOD panel, just because it was touching the loading and supporting pins. And we had some plastic deformation, as can be seen here, in the leading edge due to the extensive damage. In order to monitor degradation, we used the experimental stiffness. And to do that, we used from the MTS data, so the hydraulic machine data. We got the loading part and went to the pre-buckling part where it's more linear and calculated the slope of that curve, which in turn resulted to these two figures. So this is the 4 panels that have been tested, and in the left figure you can see the stiffness over the different loads and how this decreases, and then in the right figure you can see the stiffness behavior over time. What can be observed is that after approximately 20 kilonewton or approximately 2,400 cycles, we can see a more rapid decrease in the stiffness, which means that failure is imminent, and this is where significant damage has been introduced to the panels. So as I told you, we are going to be focusing mostly on the FBG data for this presentation, and this over here is the raw strain data, which, as can be clearly seen, you can see the different loads clearly demonstrated in the strain values. Unfortunately, this does not necessarily tell us that the panel is degraded, because strain is correlated to load. So as load increases, so does strain. In order to extract meaningful information from that and correlate it to the degradation, we create and reduce the load dependency. We created health indicators that represent the degradation behavior of the panels. It doesn't matter the specifics at this point. I just want to demonstrate that we need something or something similar to a health indicator in order to capture this degradation process. And to do that, let's compare it to our baseline, the stiffness reduction. It can be seen that at first we have a similar behavior between the stiffness and our degradation monitoring feature, that it's low, nothing major is happening. And the similar can be observed in the final parts, that when failure is imminent, we can see that our degradation index is also rapidly increasing, telling us that, okay, so maybe failure is imminent. However, when we're looking at the middle part, we see that even though the stiffness remains almost constant, we see that our indicator is indeed increasing, which may mean one of two things: that either we have some damage that is not necessarily represented in the stiffness, or that because of the increasing load, our strains still continue to capture some of the load dependency. And moving on to that, I'll just want to summarize just by discussing what benefits and what challenges we are going to face with implementing SHM and moving towards CBM. So I'll just start with the benefits and highlight those at first. So first of all, and most important, is the enhanced safety. We can have early damage detection and continuous monitoring of the structures, giving us more information in order to make more informed decision about the health status of our structures in general. Then we can go to enhance component life and sustainability. Meaning, by what I mean by that is we can have targeted inspections of parts that actually are going to fail or are close to failure, rather than wasting resources and time and replacing parts that still have a lot of operational life remaining. This will in turn increase the availability of our structures with reduced grounding time and maintenance, and only having inspections at place that needs to be inspected, which will in turn lead to cost saving because we are going to reduce the downtimes and at the same time avoid catastrophic failures of parts that need completely replacing. However, in order to go towards SHM, we are still facing several challenges. So first of all, we have extremely high initial implementation costs, both in installing the systems in already working application, but as well as having specialized software and hardware that can deal with all this increased information that are provided. At the same time, integrating the systems to current structures that are in working order, it's going to be that challenging because it will most likely require disassembling a lot of things and trying to implement over already working things. Then it comes a question of sensor durability and reliability. So what happens if our sensors fail, or are our measurements reliable? And finally, it's the point of certification, which at least for the aircraft industry, airspace industry, it's extremely high. So strict safety regulations are in place, and at the same time, the lack of actual damage information is a deterrent for implementation of SHM methodologies. And I'll just end in that note. Thank you very much, everyone, for being here.